Alright, let's work on another problem. Sorry about today being a little bit on the later side. Some stuff came up. Anyways, we're working on number, this would be 32 of our grind 75, 165 question list. 169 question list, sorry. Alright, so number 136, single number given a non-empty array of integers nums. Every element appears twice except for one. Find that single one. You must implement a solution with a linear runtime complexity and use only constant extra space. Oh, that is interesting. Linear runtime complexity. Okay. And use constant space. The size of the constraint of the values which can appear in the array are such that it would be infeasible to make an array of that size. And usually that only really works if we're dealing with strings, right, with lowercase or uppercase alphabets. So that's not the case. A set or a map would use linear space, so that's out of the question. So that really leaves maybe like a sliding window approach. Though I guess the question then becomes, how do we use the sliding window in a way that makes sense? Unfortunately, this linear runtime complexity really jumbles a lot of things. The easiest way would probably be to use, the first thing would be to use a hash map. That would be linear runtime because we just collect all the elements and then just sort through the map. And also linear space. Another solution could be to use maybe a sort to sort out the elements, and then use a sliding window of size 3, because if we use a sliding window of size 3, actually no, we should use a sliding window of size, that'd be interesting to sort and then use a sliding window, because the idea that I have in my head is that if we have a sliding window that's sufficiently large enough, we can collect all the numbers such that it would be infeasible for a number within that range to be a single number. And maybe we can take that sliding window approach and move it somewhere. Every element appears twice except for one. Every element appears twice except for one. Every element twice. Unfortunately, there's no order in this case. Having some order would be nice. Because there's no guarantee. Linear runtime complexity. I was gonna say we could maybe iterate through the array twice as kind of a stupid way to do it, but would that even be linear runtime? Basically, the idea is to scan it once, collect all numbers, and then scan it twice. Or rather, for each number we scan it, but that would be stupid. This constraint is interesting. This specific value of the array being 3 times 10 to the 4. That's not the upper and lower limits of integers in any case, right? Usually they're 32-bit integers, which makes me think that maybe there's something that we can do with that. But I'm not too sure. We know that if there's only one element in the array, then we just return 1. I think this would be size. But how do we do this? If I just realized something that I kind of forgot from before, but if they are numbers, then does Radix sort technically count as running in linear time? That's like the only situation that I know where sorting has a linear runtime. And in that case, that might be something that we can abuse. So what we do is that we do nums is equal to nums, or actually we just do a nums.sort. And this should run, let's assume this runs a Radix sort. So I believe Radix sort is like a really weird linear runtime where it depends on the size of the bucket and the base or something like that. It's a bit strange, but it is technically linear, and as long as we're dealing with numbers, right? Because only numbers can really fit into buckets, though. Yeah, maybe I could be wrong about that. I haven't delved too much into the world of Radix sort. That's not an area that we focused on in any of our studies. But let's assume this runs a Radix sort, which is linear. Then we can say let's see. Let's run a sliding window of size 2. So what are the possible, I guess, conditions to think about? We can have something like, and I'm going to be using, assuming 1, 2, and 3. So we can have 1, 1, or 2, 2, or 3, 3, whatever, right? Same thing, we handle them the same. We could also have 1, 2, or 2, 3, right? In this case, we can maybe set a flag to see if the number comes up again. Let me think. If we encounter a single number, it will always be first on the right, unless the single number is the first number in our list. If the single number is the first on our list, then that will be a problem. Show up as the first number is indeed the first. or on the right. And I meant to be show up on the left or on the right otherwise. So we need to check for that. So if the numbers don't line up and the sliding window left edge is on the first element, return that element. Otherwise, note down a flag for the number, and if it is the single number, again, then return that. This is the part that's a little bit more tricky for me, but I think this will work because of the fact that we know that all the numbers will be contained twice. So every number is twice. So we can do a var left edge equals 0, var for I in 0 to num size -2, because -1 would be the last element, -2 would be the second to last element. This doesn't make sense then. So val left edge is equal to I. Val right edge is equal to I plus 1 when nums at left edge are not equal to nums at right edge. If left edge is 0, then we return nums at left edge. So this is the special case that we talked about, where if we have a single number, or if we have a mismatch of numbers in the first tile, in the first comparison where the left edge is still at 0, then we know for sure that this doesn't make sense. That the single number is the first number. Because there is no number before it, and thus that must be the single number. Otherwise, we can set a var flagged number is equal to 0. Or we can do like an integer dot min value. If flagged number is not equal to integer min value, or actually, if it is equal to that, this will be difficult. We want to make sure that we're not kicking up the flagged number. And I think that actually in this case, it doesn't really matter. So long as the flagged number starts as something that we don't have, that doesn't exist in our array, in which case, in this case, min value doesn't exist because, though my webcam is blocking it, the minimum value is -3 times 10 to the 4, which is nowhere near the integer minimum value. So we're safe there. So we can say that otherwise, if the number at the right edge, or sorry, left edge is equal to the flagged number, return the number on the left edge. So this is the case where we've seen the number before. now return it in a discrepancy. So let's see. So if the left is not equal to the right, so in this case, like let's say 1 1 1, or it's 1 1 2 3 3. We'll do something like that. This is fine. This is the not fine. Left is not equal to right. Else flagged number is equal to nums on the right edge. So basically 1 1, nothing happens. 1 2, they are not the same. The left edge number is not equal to the flagged number, so the flagged number is now 2. Okay. So now we have 2 3. 2 3, they are the same, or they are not the same rather, and now the left edge is equal to 2, the flagged number, and therefore we return. If we had 1 1 2 2 3, this is fine. Ooh, do we want to change the increment the number by? I guess we're incrementing it by 1. Okay, so 1 2. Then since this is not the single number, then it will be the same. But in this case, the right number will get flagged. So when we hit here, now the left edge is flagged already. So that's not good. So we probably want to reset that flag. So else flagged number is equal to integer dot min value. So basically what this does is that it'll reset the flag if we ever encounter a situation where they're the same. So 1 1, that's fine. 1 2, 1 2, they're not the same. The flag is min value. It's not equal to 1, so we set it to 2. 2 2 is the same, so we reset the flag to min value. 2 3 is not the same. 2 3 is not the same, but it's not but the flag is not set. And actually this is also another edge case. So if right edge is equal to nums size minus 2, we return nums right edge. And this is the special case too, where it's on the right edge like this, right? So we have nowhere else to go, so our right edge should be there. And then we can just return -1 here. I think because Kotlin might yell at us if we don't put anything there. So I think this covers all the edge cases. Basically, we're running a sliding window of size 2 in order to get a better idea of what we're dealing with. And then we just scoot it over. Let's see. If we increase this sliding window to size 3, we will still have the same issue where we're not necessarily sure if a single number that shows up on the right edge of our window is a single number or not until we increment by 1. So I don't think there's a way to get rid of that, at least that I can think about at the current moment. Let's see. So we go from 0 to min size minus 2, and this is inclusive because Kotlin. We use our sliding window of size 2. If they are not the same, like 2 and 3, or we can do 1 2 2 3 3, and 1, 1, 2, 3, 3. So those are the three cases. So if they're not the case and the left edge is equal to 0, we return it. So that's handled. Okay, continuing on. So this case flags, we go to next. 1 and 2 for both of these. 1 and 2 are not the same. However, 1 is not equal to the min value. So we just flag 2 and then we go on our way because 2 may be our single number. So both of these have a flag of 2. Now we go to 2, 2 here and 2, 3 here. 2, 2 here is fine. We reset the flag to min value. 2, 3 here is not fine. They are not the same. And this time the left edge number is equal to the flag number, which is 2. So we return the left edge number. Handled. Finally, we get to 2, 3 in this case. And in this case, the right edge is equal to num size minus 2. Actually, it should be minus 1, right? Because we're setting the left edge to I. So this will be num size minus 2 plus 1, which is num size minus 1. And in this case, since the right edge is there and they're not the same, then we know for sure that it will be... Oh, no, we don't know for sure. Well, no. Because if it hasn't been handled yet, or it should have been handled already. Because if it was the second to last number, then it would have been handled in the prior step with the left edge and the flagged number. And so this gets handled because the right edge is there. Because in this case, we physically can't hit the last number without investigating the left side. So I think this works. And then otherwise we return -1. This is a bit of a dead case because we should always hit a number before we hit this, but I think it's just to make the compiler happy. And it might not be necessary, but I just put it there usually because the compiler usually does complain. So we assume that it's a radix sort here, which is how we get our linear runtime. It's a bit of a bit of a sus thing. I think that this is perfectly valid. I know of a couple solutions that actually require a sort. Thank you, trash can, or whatever truck is backing up. But yeah, so using a linear sort, this is probably something to explain with your interviewer. They probably know this already, maybe they don't, but radix sort is technically linear based on the bucket size, and I believe maybe it also involves the base. This is something for me to probably study on just to have a sort of a straightforward story to communicate about why radix sort is linear. But then the rest of it is just sliding window magic, basically. Let's give this a submit and see if there's any issues that we run into. And if it's especially slow, then we know that we did something wrong. 74.44% runtime and 37.59% space. I think we're fine in that case. But yeah, this is perfectly acceptable. And I mean, I've had submissions that are much lower than this in previous videos, so I think we're fine there. But in any case, I think this is where we're going to leave it. So sliding window approach along with a sort, a radix sort, in order to solve number 136 single number in linear runtime and constant extra space. Hope you enjoyed, hope you learned something, and I'll see you for the next problem.